Alright, so I don't have an engine to work on in here. Let me go look over here. Nope, I don't have one here either. So, yeah, it's gonna be one of those videos where I do a bunch of math on the whiteboard. Well, that's all I got this week. It's either that or literally watch paint dry, because all I've got to do in here for now is clean parts and paint them. So let's go back into the engine room there, into the dyno room, and see what kind of project that's coming up that I want to work on. So the thing I want to start working on fairly soon is the dyno, but not necessarily the dyno itself, and not necessarily the absorber itself. But I want to work on, what I want to work on is how the water is introduced into the absorber. Now, I've talked about the absorber a couple of times in other videos, but I'll talk about it again in this video. What it is the shaft that goes through the middle, which is also attached to the engine, is attached to a rotor in here, and it's got fins on it, and it spins. And out here on the ends are stators. So this spins, these are still, and basically what the absorber does is it spins and it stirs the water that comes in through these ports here. It stirs the water really hard, and basically the purpose of the absorber is to take the energy and the power coming out of the crankshaft of the engine and use it to warm the water up as it goes through the absorber. So again, goes in here, and then down in there, we've talked about this before, but there's a valve down in there. And what the valve does is it regulates the flow rate of water through the absorber. It can also regulate the water level in the absorber. So when the absorber is empty and doesn't have any water in it, then it basically doesn't have any load on it. As water gets introduced into the absorber and it fills up a little bit, then the absorber starts putting a load on the engine. And then what is going on is that the temperature of the water coming in through here is cooler than the temperature of the water coming out those two ports at the bottom. That's where the energy coming out of the crankshaft goes. It goes into heating the water. Now when it comes to the water flowing through this, you need a certain amount of water flowing through the absorber at any given time, at any given horsepower level. So at any rate, the higher the horsepower you're absorbing through the absorber, the faster the water needs to flow through it to carry that mechanical energy away. So what I want to talk about today is how much water flow do I need at a specific horsepower level. And what I'm going to tell you right now is so far I've just been running the water in just straight out of the garden hose. And it's kind of shaping up like that's not enough water flow, even for the budget 302, which is, it's up around 280 horsepower. So what I want to do is, going forward, I want to size a water pump for this so that I can move up, maybe somewhere between 400 and 500 horsepower. And for me here in this garage, I think that's about where I'm going to be happy stopping. And I'm not going to be doing these huge horsepower turbo engines in here. I mean, I might do turbocharger stuff, but I'm not going to be doing this huge horsepower stuff in here like you see on other videos where they make 1,000 horsepower. I'm not going there with this. It's not what I never really intended for this dyno to be used on high horsepower engines like that. But if I could go up between 400 and 500, I think that would be pretty good. So what we need to do next, before we can size the water pump that we need for this, we need to do some calculations. So let's go over the whiteboard and get started on that. Okay, so what I want to do here is I want to basically show what horsepower level I'm limited to with the water supply that I've got. And I'm not going to get into the way I cool the engine with the the heat exchanger for the coolant. That's a separate system. But for this one, we're just going to talk about what horsepower I'm limited to with the water supply that I've got. Now, there's a few parameters that are going to be important here. And one of them is the volumetric flow rate of the water, which we represented as V dot, would be the volumetric flow rate. And we're going to start out with that as in gallons per minute. And what I did was I measured that recently, and I got 9 gallons per minute. That's the water flow rate coming out of the garden hose. Another parameter that's important is the temperature, which will represent as T1, of the water going into the absorber. So measured that today, and it's early April here, and we just went through a pretty cold winter. So the water temperature coming out of the garden hose is pretty cool, and I measured that at 46 degrees Fahrenheit. And then the next thing we want to think about is what's the temperature that's going to come out of the absorber, and we'll call that T2. That'll be the temperature of the water coming out of the absorber. Now the thing that you don't want to do with a water break dyno is that you don't want the water inside of the absorber to boil, which it can. The way the absorber works is that it depends on there being liquid water inside of it. It can't be in a gas form. If it's in a gas, well, that gas has a different density and has different viscosity and a lot of different things. And you don't want it to turn into a gas, and what will happen is if it does turn into a gas, the engine will have a load on it, and then all of a sudden it kind of won't have a load on it. It'll kind of rev out of control pretty quickly. So at any rate, for the purpose of this, I'm just going to go the max temperature it could possibly be. So what we'll be doing here is we'll be looking at the absolute maximum amount of horsepower I can absorb with the water flow rate and temperatures that I've got. So the boiling temperature of water, as far as I know, is 212 degrees Fahrenheit. That's what it was last time I checked. So these are the things here that are kind of important to me right now. So the next thing we got to do is, I don't do calculations like this in imperial units. I convert all this stuff over to metric because it's just so much easier to do the calculations in. I did all this stuff earlier, and I converted that over to cubic meters per second, 0.0006 cubic meters per second. And then the other part of these calculations is that I need to convert those temperatures into kelvins. So let's turn that into, I think it came up with 280.9 Kelvin, and the higher one was 373.2 Kelvin. So what we'll be looking at here is basically what we know is that the energy that's coming out of the engine is getting absorbed by the absorber, and it's being used to heat the water. So the water out is going to be hotter than the water in. So what we need to find out is what the power flow of that water is. So what we need to look at is, what is the energy flow rate of the water into the absorber? What is the energy flow rate of the water out of the absorber? And the difference between those two things, basically it'll be a power out minus a power in. And the difference between those two powers is going to be the engine, the amount of power that the engine's making. The thing that's coming up next is a thing called specific heat. And I'm going to represent it as a C here. And it's going to be equal to 4.182 kilojoules per kilogram dot Kelvin. So what the idea there is, and that's the specific heat of water. So the importance of that is that, let's say you have a kilogram of water and it's at a certain temperature. This will tell you basically how much heat energy that water contains. And basically at that same mass level, if you increase or decrease the temperature, then you'll be increasing or decreasing the amount of heat energy that's in that mass of water. We know what our volumetric flow rate is here, but for these calculations, we need to be looking at something called a mass flow rate. We'll represent the mass flow rate as an m dot, and that will be equal to the volumetric flow rate right there times the density of the water. We'll represent that as rho. And that's, so what we got there is 0.006 meters cubed per second times 998, and I'm running out of room, 998 kilograms per meter cubed. So that's the density of the water, 998 kilograms per meter cubed, and what we end up with there, if you multiply those two together, basically you can round it up to about 0.6 kilograms per second. So now that we know how quickly the mass is flowing through it, and we know the change in temperature, and we know this property of the fluid, at that flow rate, we can calculate how much power you need in order to change the inlet temperature from here to here. So let's do that next. What we want to find out is what's the power of that. And we'll just represent that with a P because I don't have a ton of space here. And to calculate the power, you need to multiply the mass flow rate times specific heat. Just stick with it. Let's see. So we got the power as the mass flow rate times the C, and I forgot to put in here the delta T, but that goes in there too. But this, we'll just have to deal with it. So we got a mass flow rate of 0.6 kilograms per second, and that's going to be times 4.182 kilojoules per kilogram, and then we're going to do dot the delta K, which came out to be 92.3. That's the difference between those two values. And what we end up with is a power level of 231.6 kilojoules per second. Converting that over into horsepower, we get that equal to 310.5 horsepower. Why is that number in reality going to be probably 30 or 30 horsepower less than that maybe? Well, that's because I can't go to that temperature with it. If I go to that temperature, I'll be running right at the ragged edge of it boiling the water. Well, I will be boiling the water at that point. But I can't go that high with the temperature. So this number is going to be lower than this here. Now, what I was talking about before is, how do I size a pump for this? Well, I can take these equations and move things around, and that's what I did. I built a spreadsheet where I can enter different values in for this and not have to do all this by hand each time, so I can quickly change things. And I wrote it in a way that I enter in how much horsepower I want to absorb, what the water inlet temperature is going to be, and what the water outlet temperature is going to be, and use those values to calculate what a volumetric flow rate I need. And once I know that, I can size a water pump for it. So let's go inside. We'll take a quick look at that spreadsheet and enter in some values and kind of see what kind of a water pump I need. Okay, so here's the spreadsheet that I made up for this, and basically there's that number, that horsepower number we were looking at before, and our inlet water temperature, our outlet water temperature, and over here I've got the things that are either constants or calculated. And what you do is enter in the horsepower level that you're looking at and the water inlet temperature and the water outlet temperature, and it'll tell you basically how many gallons per minute you need at that flow rate. Now I noticed that before I inputted a value of 9 there to get this output, and I'm guessing there was just a bunch of I did some rounding in the calculations, in the hand calculations before, and then this one's not doing any rounding, so it makes it a little bit different. I'm guessing that's where that's coming from. So let's start out. Let's start out where I think the 302 is at right now, which is probably around 280 horsepower. And let's put in some more realistic values for this here. Like more realistic summertime or springtime values might be that. And like I said, we don't really want to get anywhere near 212, so let's say 175 degrees water outlet temperature. I might be able to tolerate that. And you can kind of see, even at that, with these values here, I'm a couple gallons per minute low for that horsepower level. So and the other thing is, you may have heard me remark in the past that as the engine RPMs go up, that I tend to have a little bit more trouble controlling the engine at those speeds. Well, the other thing that's going up with the RPM tends to be the horsepower, so it doesn't continue to go up. But as it goes up, and the problems I start running into happen around 4,500, and I have a really difficult time controlling the engine above that engine speed, and it's probably because the horsepower has gone above what the dyno can absorb with that water flow rate. But that's just a hypothesis at this point. I'm not 100% sure, but judging by these numbers, yeah, I'm kind of low on water flow at that horsepower level. Now what I've done over here, I just added this in, and these are a couple of different flow rates that I just did a search around, and when I started building the engine dyno, I remember there were a couple of different ways to estimate how many gallons per minute you need for your absorber. And this one here is like 1 gallon per minute for every 20 horsepower. So basically you take that and divide it by 20, and then you get that. And these are a couple of standards that are out there. I don't, it's but you can kind of see that 14 there. That's not real far away. That's only 2 gallons per minute away from that one there that I calculated. So yeah, so at any rate, these are a couple different ways. This one here to me seems a little, at least for what I'm doing, this one here seems kind of high for me. I'm not going to say that for other, and I'm not going to say that's true for everybody's. I'm not going to say. I just think that for my particular dyno, that seems like kind of a high number to me. But this one here kind of seems about right. So I kind of, that's I should have put the gallons per hour there too. But basically, this is what we got. Now, so these seem sort of okay to me, these numbers here. But let's see what kind of flow rate we need to, let's say I'm thinking kind of the most I'm ever going to want to have, the most that I'm ever going to want to deal with on that dyno is maybe around 450. But let's say 500, just to say 500. So we need about 21 gallons per minute. And that equates out to about 1,200, or nearly 1,300 gallons per hour. Yeah. So I know there's pumps around roughly that size. I've seen, the local, there's some stores around here that sell water pumps like that. And I think they're either called like sprinkler pumps, or maybe it's either like a sprinkler pump or it's maybe like a shallow well pump. I think there's some that flow roughly that number there. And they range in, I've seen them start around like 150 and they go up from there. So maybe a sprinkler pump or maybe a shallow well pump might be a good option there. And then rather than run the Dyno water off of the garden hose, I can run the Dyno water. I can run the Dyno water into the water tank that I have, which I haven't shown anybody yet. Which maybe we can have a look at that sometime. And it's a 275 gallon tank, so it's basically an IBC tote that I have out there. I think they're 275 gallons. So how long would I be able to run at 22 gallons per minute? So I'd be able to run full load for about 12 minutes, which would be plenty of time. So, okay, anyway, that's where I'm at. Now, I had to do math today, so it's not something I do very often. And I'm sure there's a good possibility I may have made some mistakes there, so, but and I usually don't notice my math mistakes until I'm editing the video. So, yeah, if I notice mistakes, either I'll try to correct it by commenting over the video, or I'll say something about it in the description. So, I'm not really sure when the Kubota is going to be back. We took it down to the machine shop earlier this week, so yeah. I'm not sure when it'll be back, but hopefully it won't be too long, and then we can get back out there and start working on that and get that back together. Yeah, so anyway, that's about all I got for this week, and I guess I'll see you next time.